Welcome to MANATV classes. Today's topic is vector space, vector subspace and linear combination of vectors. So, this is by Dr. S. Nagendra, lecturer in mathematics, Government College for Men, A, Kadapa. So, I hope that you are all aware of the concepts of ring, commutative ring with unity and field division ring. So, these are the concepts that you would have studied in the 5th paper of 5th sem. Now, these concepts vector space, vector subspace and linear combination of vectors, which we are going to deal in this class, they are the part of 6th paper of 5th sem. So, having studied about the concepts which I illustrated just now, I hope these concepts would be very easy to understand. So, the major purpose of the concept of vector space is that it has good applications in the study of quantum physics, quantum sciences and image processing. So, the total application for all these applications, the basic concept is vector space. So, let us start with the concept of vector space. So, what is the definition of vector space? So, the definition goes like this. So, start with a field F. So, let F plus dot be a field and V be any non-empty set associated with two binary operations, namely plus, so which is from V and dot, which is from F cross V to V. So, please understand. So, we have a field structure F and a non-empty set V, which is already associated with two binary operations, which one is plus defined from V plus V cross V to V and dot, which is defined from F cross V to V. Then V is called a vector space over the field F if, so the bracket V over F plus dot satisfies the following axioms. So, let me repeat once again. So, what are the entities that we are taking? First, we are considering the field F, next a non-empty set V having two binary operations which are plus. So, this is defined from the V cross V to V and dot, which is defined from F cross V to V. Then the set V over the field F is called vector space if it satisfies the following axioms. So, axioms already you would have understood because you have been acquainted with the several axiomatic systems from the second year onwards, like group, abelian group and normal subgroups and rings, fields, etc. So, I need not explain what is the meaning of axioms. So, let us look at what are the axioms. So, the first axiom is V plus is an abelian group. So, first axiom, the condition that has to be satisfied by V is the V with respect to addition with respect to plus has to be an abelian group. The second axiom is for every A belonging to F and alpha belonging to V, you find the product A dot alpha, that product should be in V. So, of course, this cannot be called exactly product because we are taking A from F and alpha from V, both are from different sets. So, that result A dot alpha should be in V. So, this is the second axiom. Let us look at the third axiom. For every A comma B belonging to F, alpha comma B belonging to V. So, I am taking two elements from F field and two elements alpha beta from V. So, there are four conditions under the third axiom. So, the first one is A dot alpha plus beta should be equal to A dot alpha plus A dot beta. Second one is A plus B dot alpha should be equal to A dot alpha plus B dot alpha. The third condition is A dot B dot alpha. So, I am putting A dot B in the bracket. So, A dot B dot alpha should be equal to A dot B dot alpha, which is also equal to B dot A dot alpha. And fourth one, finally 1 dot alpha is equal to alpha dot 1 should be equal to alpha. So, where 1 is the unity in F, because F is a field. So, it has unity. Unity is nothing but multiplicative identity. So, that is called unity and it is denoted by 1. So, when you take the product with 1 and alpha and 1, the result should be alpha. So, please note that these are the 3 axioms that have to be satisfied by V, if at all it has to be a vector space. Apparently, even though there are only 3 axioms, but you can see there are more, because the first axiom V plus is an abelian group, this itself has 5 axioms. So, dear students, please remember what are the 5 axioms. So, first one is the closure, second one is associativity, third one is identity axiom, fourth one is the inverse axiom, and fifth one is abelian property. So, the first axiom itself involves 5 sub axioms, and second one is as it is. The third one you can see, third itself involves 4 conditions. So, totally if at all you have to verify whether V is a vector space. So, how many you have to verify, how many conditions, how many axioms you have to verify? 5 plus 1 6 plus 4 totally you have to verify. 10 conditions you have to verify so that V is a vector space. So, is the definition clear? Okay. So, this again an axiomatic system, okay, followed by these 10 rules and regulations. So, let us look at some important points regarding a vector space. So, if V over F is a vector space, then the elements of V are called vectors. So, here we have 2 sets, V and F. So, the elements of V are called vectors and elements of F are called scalars. So, is the difference clear? So, the elements of V are called vectors and elements of F are called scalars. So, the notations and notions are themselves are derived from the concept of vectors and scalars, which we would have studied in physics and sciences, etc. It is a type of generalization. Okay. So, let us note some few points. So, the first point is, so we defined 2 binary operations in V. So, one was plus. So, that plus is called vector addition, and the second one was dot. So, that is called scalar multiplication, because it is not exact multiplication. We are multiplying a member of F, a scalar, with a member of V, a vector. So, that is why it is called scalar multiplication. So, the second one is called is if alpha belongs to V, then as we said V plus is an abelian group. So, it has additive inverse. So, its additive inverse is denoted by minus alpha, which is again in V. And the third condition is, third point to be noted is, as we know it has additive identity also. V has additive identity because it is an abelian group with respect to addition. So, that is denoted by 0 and a bar over it. So, it is read as 0 bar, and we have and it is called 0 vector of V, because elements of V are themselves are called vectors. So, in particular this is called 0 vector of V. The fourth point is, so please note that F is a field. So, field means it is a commutative ring with unity and every non-zero element having multiplicative inverse. So, this also F also has a as an additive identity. So, please note that V already has additive identity, that is denoted by 0 bar, and it is called 0 vector of V, whereas the additive identity in the field F is denoted by simple 0, no bar and all, and this is called 0 scalar of the field F. So, please make note of these differences, students, please make note of these differences. So, the additive identity in V is called 0 vector and denoted by 0 bar, and additive identity in the field F is called 0 scalar of the field F and denoted by simple 0. Okay. So, if these points are clear, let us go to the simple definitions. Okay. So, even though we are specifying F is a field, but as per my knowledge throughout this paper, we consider only either real numbers as F, set of field of real numbers, or field of complex numbers. So, if F is equal to R, then the vector space V over R is called real vector space. If F is equal to C, the field of complex numbers, so you would have already studied in the 5th paper as an examples for fields, set of real numbers, set of complex numbers. So, if F is equal to set of complex numbers, then V over C is called complex vector space. So, dear students, please note that these are the only not fields. So, we have so many fields, like we have especially finite fields. So, among them also, over them also we can have vector spaces. So, that study is also very much available in the reference books. But for the sake of simplicity and understanding, we consider throughout this paper F as set of real numbers, then the vector space is called real vector space, or equal to set of complex numbers, then the vector space is called complex vector space. Right. Let us observe a simple theorem about vector space. So, this gives some simple results about vector space. So, if you would have studied this type of theorem already in the ring theory, the 5th paper, so it looks similar to. So, what the statement of this theorem is? So, let V over F plus dot be a vector space, 0 bar and 0 be the 0 vector and 0 scalar, just now we mentioned respectively. Then the first result is A dot 0 bar is 0 bar for every A belonging to F. So, you have 0 vector and you are multiplying by any scalar, you multiply 0 vector by any scalar, the result is again 0 vector. The second condition is 0 dot alpha is again 0 bar for every alpha belonging to V. The third condition is A dot minus alpha is minus A alpha for every A belonging to F and for every alpha belonging to V. Fourth one, minus A dot alpha, which is again minus A alpha for every A belonging to F and for every alpha belonging to V. Fifth one, minus A dot minus alpha. So, that comes out to be A dot alpha for every A belonging to F and for every A alpha belonging to V. So, let us look at the simple proofs of these statements. So, the first one, so what the first one states is A dot 0 bar, A dot 0 bar. So, if you observe this statement, I have to prove that this is equal to 0 bar. Okay. So, start in this way. So, just take A dot. So, I am writing the 0 bar as 0 bar plus 0 bar. So, can we write this? Yes, because 0 bar is the additive identity in V, 0 bar is the additive identity in V. So, I can write 0 bar as 0 bar plus 0 bar, right. So, by the distributive law, the third condition of the vector space, A dot alpha plus beta. So, that gives A dot 0 bar plus A dot 0 bar. So, finally, we are getting A dot 0 bar equal to A dot 0 bar plus A dot 0 bar. And you can see we are in the group structure. Even though vector space, it is a vector space, but vector space with respect to addition is a group, is an abelian group for the in fact. So, in a group structure we can always use cancellation laws. So, when I cancel A dot 0 bar, A dot 0 bar on both sides, I get A dot 0 bar equal to 0 bar. So, that completes the first result, and you can see there is nothing special about A. So, I can write here for every A belonging to A. Is it clear? So, the next one. So, what is the next second one? So, the second one is 0 dot alpha. So, you take this, you multiply this, the scalar 0 with any vector alpha of V and see what is the result that you get. Repeat the proof of 1 with the scalar 0. Now, I apply the property of additive identity to the scalar 0. How? So, write 0 as 0 plus 0 dot alpha, which is nothing but again we are in the field. So, we are in the vector space. So, I can apply A plus B dot alpha, which is nothing but A dot alpha plus B dot alpha, that is 0 dot alpha plus 0 dot alpha. So, by the result we are getting 0 dot alpha equal to 0 dot alpha plus 0 dot alpha, which is again we are in the group structure with respect to addition. So, I can apply cancellation laws. So, I can cancel these two. So, what do I get? 0 dot alpha equal to 0. So, this completes the second one. Let us run proof of the third one. So, what is the third one? So, I have to prove A dot minus alpha is minus A dot alpha, of course for every A and for every alpha. So, please understand, just now we mentioned that minus A dot alpha is nothing but the additive inverse of A dot alpha. Just now we mentioned in the points to be noted. So, I have to show that the additive inverse of A dot alpha is nothing but A dot minus alpha. So, it is enough if you verify the additive inverse property for A dot alpha. Is it clear? So, I am going to do that only. So, consider, you simply calculate what is the value of A dot alpha plus A dot minus alpha. So, what is this equal to? Again apply the condition of vector space, we are in the vector space. This is of the form A dot alpha plus A dot beta. So, by the first one of third condition, this is A dot alpha plus minus alpha. But what is the value of alpha plus minus alpha? Just now we said minus alpha is the additive inverse of alpha. So, when you add an element to its additive inverse, the result will be 0 vector. So, this is A dot 0 bar, but what is A dot 0 bar? Just now the first result shows this is 0 bar. That means, when I add A dot alpha with A dot minus alpha, I am getting 0 vector. And you can see similarly the other way also. You can see if you find out A dot minus alpha is plus A dot alpha, also you get 0. So, that implies the additive inverse of A dot alpha, which we denote it by minus of A dot alpha, is nothing but A dot minus. So, that completes the third property. Again fourth one, the fourth one states minus A dot alpha is minus of A dot alpha. It is a similar proof. Only thing you have to prove is verify the additive inverse property for A dot alpha, now with minus A dot alpha, not with A dot minus alpha, now with minus A dot alpha. Do the same thing and apply the additive inverse property of the field F, you get back to 0. Students, is it clear? Now, I am proceeding to fifth one directly. So, the fifth one states, minus A dot minus alpha. It is very simple. I need not do any type of axioms, any type of conditions I need not use. Simply I will use the results 3 and 4. So, let me use the third result. So, what it says? A dot minus alpha. So, assume for the time being this is A and this is minus alpha. So, what the result says? A dot minus alpha is minus A dot alpha. So, I can write from 3, this is minus of A, in place of A I have minus A dot alpha. So, once again try to assume this is A dot minus alpha. So, third result says this is minus A dot alpha. Now, what the fourth result says? Minus A dot alpha is nothing but minus A dot alpha. So, we get minus of A dot alpha. But what is minus of A dot alpha? It is the inverse of A dot alpha, which is nothing but A dot alpha. So, that is what the fifth result is very simply proved using third result and fourth result. So, this is the simple properties of vector space, okay, so which are very easy to prove and understand. So, let us go to some examples of vector space. Before going further, let us look at some examples which are vector spaces and which are spaces. So, the first example, even though the verifying examples as vector space and exercises is a very lengthy process, but in the short span of time, so I have chosen only simple examples. So, take V is the set of real numbers and F is also the field of real numbers. So, please note that I am taking both as set of real numbers, and where plus is the usual addition of real numbers and dot is the usual multiplication of real numbers. So, now observe that now R over R with respect to this addition and multiplication is a real vector space. So, my dear students, is it easy to see? Is it easy to observe? So, let me explain. So, let us go to the first condition. So, first condition we have to verify that V plus is an abelian group, V plus is an abelian group. Now, we are taking V is R, we know that R is a field, R is a field with respect to usual addition and multiplication of real numbers. So, field means it is already a commutative ring with unity. So, it is an abelian group with respect to addition. So, the first condition is automatically satisfied. Now, what about the second condition? For A belonging to F and alpha belonging to V, A dot alpha belongs to V. So, that is again closure with respect to multiplication, because here dot is the usual multiplication of real numbers. That also follows because R is a field, because field is a commutative ring, and in the commutative ring properties it is also one of the properties. Next, if it comes to the third properties, third lo manku we have 4 axioms. So, A dot alpha plus beta equal to A dot alpha plus A dot beta. So, do you identify this property, my dear students? Yes, exactly, these are the distributive properties, distributive laws which come under rings. And A plus B dot alpha, once again A dot alpha plus B dot alpha, it is again another distributive law. So, are you able to understand? And A dot B dot alpha, which is A dot B dot alpha or B dot A dot alpha, which is the associativity with respect to multiplication, which automatically follows from the field structure, from the ring structure. And finally, 1 dot alpha, and 1 is a unity, multiplicative identity. So, the property of multiplicative identity implies that 1 dot alpha, alpha dot 1 is alpha for every alpha belonging to R. So, do you understand, the field structure automatically implies that R over R is a real vector space. So, my dear students, is it clear, right? So, there is nothing special about set of real numbers. So, you yourself can make a general statement by this time. So, what is that general statement? So, can anybody guess? There is nothing special about the field of real numbers. You take any field F, now consider the vector space F over here. By whatever explanation I have given just now, this has to be a vector space. This has to be a vector space. Okay, so that you can understand later. Let us go to the next example. So, now take V equal to same R, set of real numbers, and F is the set of complex numbers, field of complex numbers I am taking now. With respect to, now plus is the usual addition of real numbers and dot is the usual multiplication of complex numbers, usual multiplication of complex numbers, because here you have to multiply a complex number with a real number. So, that is naturally it is nothing but multiplication of complex number, it is taken as. Now, do you see that, is it a vector space? Is it a vector space? So, no doubt the first axiom is satisfied, that is R plus is an abelian group. How does it follow? Again from of R, no problem. Now, where the problem comes? In the second axiom. What is the second axiom? Closure with respect to scalar multiplication. Here scalar multiplication is the usual multiplication of complex numbers. So, I have to multiply a complex number with a real number. So, you take an example for I, which is the complex number, and 1 belonging to R. So, you multiply them I dot 1, you get I. But this has to be in the V, which is set of real numbers, but I is not a real number, we know. I is the complex number, I is the imaginary number. So, I is not a member of R. So, this is not a vector space. So, set of real numbers over the field of complex numbers is not a vector space. So, in the available time I have given an example for a vector space and an example for a vector space which is a set which is not a vector space. So, there are so many exercises and verifications, examples in any textbook on this topic you can see. So, for the time being I am giving these problems as a homework for you. So, let me explain. So, to total setup has to be like this. So, you have to be given V, you have to be given F, and what is addition, what is scalar multiplication. So, these 4 aspects have to be covered, then you must be asked whether it is a vector space, prove that it is a vector space or verify whatever it is. Now, look at the first problem. So, let V is, I am taking set of all ordered pairs x comma y, where x and y are real numbers, and F is the usual field of real numbers, and plus and dot are defined on V as, so I am adding an addition on V as, so take 2 ordered pairs x comma y, a comma b. So, how they are added? X plus a comma y plus b. So, simply coordinate wise addition, first coordinate is added to first coordinate, second coordinate is added to second coordinate. Next, how the scalar multiplication? C dot x comma y, how is it defined? It is simply C x comma C y. So, you multiply C by both coordinates. So, now I am asking you to verify whether V over R plus dot is a vector space. So, you try to verify all the axioms and see whether it is coming out to be a vector space. So, I hope you would do at home. Next problem I am going to give is the set of functions. So, if you see any textbook on this topic, you have plenty number of problems covering different categories of vector spaces, like number sets, as we have seen the tuples, coordinates, pairs, ordered pairs, and this is category of functions, and you can see matrices and so many types of examples, types of problems you can see. So, the second problem goes like this. So, start with V, which is set of all functions defined on closed interval 0 comma 1 to the set of real numbers, nothing but real valued functions on closed interval 0 comma 1, where f is a function. So, I am simple condition I am putting is f is a function, and take f equal to the same field of real numbers, and what are the plus and dot? They are defined as follows. So, define f plus g of x is f of x plus g of x, and c dot f of x as c dot f of x for c belonging to R and f belonging to. Now, again I ask the question that verify whether V over R plus dot is a vector space. So, please understand, if you do these 2 problems, certainly you would know the procedure how to show the given set over the given field is a vector space, and at the same time you would understand where under what circumstances one of the axioms would be failed, so that you can easily identify and make sure that that is not a vector space. So, before ending this topic, so I want to show the significance of addition defined in the first problem, that is x comma y plus a comma b, which we are defining as x plus a y plus b. So, if you see, if you observe the definition of V is nothing but R cross R, because one first coordinate we are taking from real numbers and second coordinate we are taking from the real numbers, both x and y. So, adding, we are adding. So, suppose I have x and y here and y plus b, the coordinate wise addition, but how one would have got this idea is nothing but the parallelogram law, the simple parallelogram law of addition. So, simply draw a parallelogram covering these 2 vectors. Now, find out the coordinates of this diagonal. So, this comes out to be a plus x comma y plus b. How? Because the important property of parallelogram is the diagonals bisect each other, diagonals bisect each other. So, use that property, and this already we know this is 0 comma 0. So, using this fact and using the formula for midpoint, you can easily find out that this vector corresponds to a plus x and y plus b. So, this is the geometrical significance of the V given in this problem. So, in the first topic we defined what was a vector space and certain points to be noted and some examples and a simple theorem about vector space. So, this ends the first topic. So, let us proceed to the next topic. Now, let us discuss what is a vector subspace, which is the second topic of today's class. So, in the study of these algebraic structures, it is usual to study a substructure of a given structure. So, my dear students, you would have noticed in the third semester also, once you would have studied group, you would have studied subgroup. Is it clear? Idi chadivi untama? Yes. Once you have studied ring, you would have studied subring. Once you have studied field, you would have studied subfield. These are all structures. So, similarly, we also study vector subspace or simply subspace, upantaraalamu antam. So, the definition goes like this. So, let V over F plus dot be a vector space and W be a non-empty subset of V. So, we are calling subspace kabatti you have to start with a non-empty subset of V, which we are denoting it by W. So, if W over F, so take W as a part over the field F with respect to same addition and multiplication, scalar multiplication is a vector space, then W is said to be subspace of V. So, let me repeat once again. So, you consider the total structure with respect to W. So, if I draw the picture, this is V, suppose this is V, now this is W. Now, consider only with respect to this W over F with plus dot. So, if that sub of V is a vector space, satisfies all the conditions of vector space, then W is called subspace of V. So, is the definition clear? Okay. So, take a subset, non-empty subset, you know, because it should have some elements, then only we can talk about anything. So, that is why we are starting a non-empty subset W. So, if W itself satisfies all these axioms of vector space, then W is called subspace of V. So, let us look at some simple examples of subspaces. So, take any vector space V and take W equal to 0 bar. So, what is the 0 bar? This is the 0 vector of V. So, I am starting W to be that simple 0 bar. Now, do you see that it is a subspace of V? Yes, because with 0 bar you can see all the axioms will be satisfied. 0 bar is the additive identity and it is itself self inverse and all the axioms will be satisfied, because 0 bar dot 0 bar is again 0 bar and all the distributive properties will be satisfied, and 1 dot 0 bar is again 0 bar. So, it is trivial to see that it is a subspace of V. Next, the second one, now take W to be V itself, because we know a set is a subset of itself. So, you can take W is V and you can see V is already vector space. So, here V is a subspace of V itself. So, till now we got two examples for subspaces, one is containing only 0 vector and another is the total vector space V. Even though these are examples, good examples for subspaces, but we consider them as the trivial subspaces of V. Trivial means they are very easy to identify, they are not very significant, that is the meaning. So, these are trivial examples of subspaces of V. But this is not our particular interest. Our interest is to find for a given vector space V, how to find non-trivial subspaces. So, how to verify non-trivial subspaces of V. So, of course, it is very difficult, because while verifying vector spaces itself, I told that it is a very lengthy process. You have to verify totally 10 axioms, 10 conditions. So, here also for a given W, you have to verify all the 10 axioms. So, which is a laborious process. So, mathematicians thought this work should be reduced. So, they have given, for the sake of convenience, for our sake of convenience, they have identified a necessary and sufficient condition for a non-empty set W of a vector space V to be a subspace of V. So, my dear students, I hope you understand what is the meaning of necessary and sufficient condition. It is a if and only if condition, a double implication. So, what this necessary and sufficient condition, please read it. For every alpha comma beta belonging to W, A comma B belonging to W, A alpha plus B beta, we have dot in between, A dot alpha plus B dot beta should be in W. So, if at all W has to be subspace of vector space V, this condition has to be satisfied. So, if you want to state the same statement in if and only if means that goes like this. So, W is a subspace of V if and only if for every alpha beta in W, A comma B in F, A alpha plus B beta should be in W. సో ఈ ఒక్క కండిషన్ మనం వెరిఫై చేస్తే చాలు W సబ్స్పేస్ అని కంక్లూడ్ చేయవచ్చు. సో చూడండి 10 యాక్సియమ్స్ ఆర్ రెడ్యూస్డ్ టు ఓన్లీ 2. మరి ఇది ప్రూవ్ చేయాలి మనం, సింపుల్గా వాడడానికి లేదు. ఓకే, సో వీ హ్యావ్ టు వెరిఫై ద ట్రూత్ ఆఫ్ దిస్ స్టేట్మెంట్ మీన్స్ వీ మస్ట్ సప్లై ద ప్రూఫ్. ఓకే, సో ద ప్రూఫ్ గోస్ లైక్ దిస్. సో please note that it has two parts because it is a if and only if condition. So first we have to assume W is a subspace of V and prove the condition. Next assume the condition and prove W is a subspace of V. So first part we are assuming W is a subspace of V. So start with if W is a subspace of V. Already W is a subspace. W is a vector space. W is a vector space. So it is closed with respect to addition and also closed with respect to scalar multiplication. So after all, for alpha beta belonging to W and A comma B belonging to F, you find out A dot alpha and B dot beta. Just now we said it is a property of vector space. So the combination A dot alpha plus B dot beta should be in W. Do you understand? It follows very simply from the conditions of vector space, right? Now let us go to the second part. So conversely, now we have to assume the condition is true. So conversely, now if for every alpha beta belonging to W and A comma B belonging to F, assume that A alpha plus B beta belongs to W is true. Now what we have to prove now? W is a subspace of V. So to ensure that W is a subspace of V, by definition we have to show that W is a vector space. W over F is a vector space. Right. So for that what we do is start with simple combinations. You see, take A equal to 1 and B equal to 1. So what the combination becomes? 1 dot alpha plus 1 dot beta, which is nothing but alpha plus beta. So which belongs to W, because మన condition అదే ఇచ్చాడు సార్, for every A B for every alpha beta. I am only changing the values of A and B. So this is closure with respect to addition. Next, take A and B as 0. So that comes out to be 0 dot alpha plus 0 dot beta. Just now we showed the combination 0 dot alpha is 0 bar, 0 bar plus 0 bar is 0 bar, which belongs to W, again from the given condition. Now take A equal to minus 1 and B equal to 0. So we get minus 1 dot alpha plus 0 dot beta, which is minus alpha. So from the given assumption, minus alpha belongs to W for every alpha belongs to W. So first one we have showed additive identity is in W, the 0 vector is in W, and additive inverse for every element of W we ensure. Now next take A equal to A and B equal to 0. So what do you get? You get A dot alpha, which is closure with respect to scalar multiplication, that we proved. So we proved closure with respect to addition, with respect to scalar multiplication, additive identity exists, inverse exists. Now what else? All other axioms you can see, these are all equations, associativity with respect to addition, abelian property with respect to addition, and all distributive laws, they follow automatically as they are true in V, because they are already true in V. So automatically they follow that they are also true in W. Is it clear? So hence the theorem. So we verified all the conditions of vector space, therefore W is a vector space, so W is the subspace of V. So my dear student, do you understand now? By using that simple condition, we verified all the 10 axioms of vector space. Now we can use this result to verify whether given set is a vector subspace of given vector space V. Now shall we do some problems, right? I have taken the V which we had given as a homework. Okay. So you do that homework part. Now we will only see the subspaces of V. So again, whatever we have defined there, V is a set of ordered pairs x comma y, and F is a set of real numbers, and addition is defined and multiplication is defined. Now verify whether the following subsets are subspaces of V. The first one I am taking as W1 is 0 comma 0, the set consisting of only 0 comma 0. So now what is this 0 comma 0? Can anybody identify? Yes, this is the additive identity in V. This is the 0 vector, 0 bar of V, nothing but just now I had shown in the figure, that is origin. So, just now we told that from after the definition of subspace, the W consisting of only 0 vector is always a subspace of V. So, clearly W1 is a subspace of V as it contains only 0 vector. Is it clear? This is a trivial subspace, just we talked about this. Now, take W2 is set of all ordered pairs having y coordinate as 0. So, put x and y coordinate as 0 where x belongs to R. Now, let us see whether it is a vector space. So, we again use that necessary and sufficient condition which we proved just now. So, start with alpha beta, alpha is x comma 0 and beta is y comma 0 in W2 and take A and B in R. Now, verify the combination A dot alpha plus B dot beta, A dot x comma 0 plus B dot y comma 0, use the definition of scalar multiplication and addition. So, that comes out to be Ax plus By comma 0. But do you see that this is again x part is there, y coordinate is 0. So, this belongs to W2. So, that is the definition of W2, y coordinate second coordinate has to be 0. So, this belongs to W2. So, is our necessary and sufficient condition satisfied? Yes. So, W2 is a subspace of V. Next, look at the third one. So, before going to third one, look at the geometry of the second one. So, as I said, the R cross R just now we had seen is the xy plane, with origin 0 comma 0. Now, what is this W1 represents? W2, W1 is simply origin, W2 it is x comma 0, y coordinate is 0, x coordinate varies. So, what does that indicate geometrically? So, is it not x axis? So, this is x axis. So, W2 is nothing but x axis. So, x axis is a subspace of xy plane R cross R. Next, W3. So, what W3 contains? Set of all x comma mx where xm are real numbers and m is a constant one. Again you take alpha beta in W3 and verify A dot alpha plus B dot beta and look at the combinations, you can see you get Ax plus By comma m into Ax plus By. Again you can look at the combination W3 and the vector which we got here, both are similar. X coordinate place lo m untundo, the same should be multiplied by m. So, this belongs to W3. So, W3 is a subspace of V. And again, my dear students, do you identify this W3 geometrically? W3 geometrically, can anybody? Yes. So, whatever x I have, y should be m times x. So, is it not the line passing through origin? This is y. So, how any point on this line looks like? It is x comma mx. So, we got two subspaces of three, of course. The first one is a trivial subspace. The first one is x axis and second one is the line passing through origin, and finally W4 which consists of ordered pairs x comma 1 where x belongs to R. Now, try this, you can see for alpha x comma 1, beta y comma 1, you can see A alpha plus B beta comes out to be Ax plus By comma 2. You are getting comma 2, the second coordinate you are getting as 2, but manaku second coordinate em undali 1 undali. So, this does not lie in W4, this does not belong to W4, hence W4 is not a subspace of V. So, my dear students, so in the second topic we discussed the definition of subspace of a vector space and some trivial subspaces and what is the necessary and sufficient condition for a subset to be a subspace of V, and we also supplied the proof and some examples verifications in case of R cross R. So, this concludes the second topic, subspace. Next, let Next topic is linear combination of vectors. Having studied vector space and subspaces and so many examples, let us look at what is linear combination of vectors. So, simply have a vector space V over F and consider alpha 1, alpha 2, etc., alpha n belonging to V. So, I am taking n vectors in V. Now, prepare any vector gamma, I am denoting it by gamma. How gamma is defined? Gamma equal to A1 alpha 1. So, I am A1 dot alpha 1 plus A2 dot alpha 2 and so on An dot alpha n. So, I am simply multiplying these n vectors with n scalars where A1, A2, An belong to F. So, I am getting a resultant vector as gamma. So, this gamma is called linear combination of the vectors alpha 1, alpha 2, etc., alpha n belonging to V. So, do you understand? We are taking set of n vectors and set of n scalars and we are making a combination of them. So, that resultant vector is called linear combination of vectors alpha 1, alpha 2, alpha n belonging to V. So, please note that this gamma belongs to V. Is it clear to students? Is it clear, my dear students? Because we are in the vector space, closure with respect to addition and scalar multiplication is automatically satisfied. So, that is gamma. So, the gamma belongs to V. So, please understand, in case of why is it called linear combination? It is combination, no doubt. Why is it called linear combination? Let me show you in R cross R. So, if you take two vectors, so this is x axis, y axis and 0. So, if you take two vectors, say alpha 1 and take another vector alpha 2, this is alpha 2, this is alpha 1. So, if you take A dot alpha 1, how A dot alpha 1 looks like? It is, it lies on alpha 1. I am taking A times alpha 1. So, if this is alpha 1, I am taking A times. So, it may be an extension or regression. So, suppose if it is an extension, this is A alpha 1 and similarly B alpha 2. So, this is B alpha 2. Now, I am adding them A alpha 1 plus B alpha 2. Okay. Now, prepare the parallelogram and see that the diagonal, the resultant diagonal, this represents A alpha 1 plus B alpha 2. But ఇది ఎక్కడ ఉంటుంది? Where does this vector lie? Please note that this lies on alpha 1 plus alpha 2, because alpha 1 ఇక్కడ ఉంది, alpha 2 ఇక్కడ ఉంది. So, this is alpha 1 plus alpha 2. So, whatever A value you take and whatever B value you take, the linear combination has to lie on the same vector alpha 1 plus alpha 2. That is why it is called linear combination. Okay. So, this is the definition of linear combination of vectors, and we have linear span also, all possible. So, suppose you are given a non-empty subset of a vector space V, then linear span is defined to be all possible linear combinations of vectors in S. Okay. So, this can be studied in detail in the later classes. So, let me pose some few points about this linear span. Suppose if S is vector consisting of only 0 vector, then you can see L of S is only 0 vector, because whatever combinations you take with 0 vector, the result will be a 0 vector. And you can see that S is always subset of L of S, because by making these scalars as 1 1 1 1, you get all the vectors. And another important result is, if S is a subset of a vector space of V over F, then L of S is always a subspace of V. L of S is a subspace of V. So, please note that this is again we are going to prove that something is a subspace. So, to prove something is a subspace, which criteria should we use? Again, necessary and sufficient condition, which we proved just now. So, I am going to use the same method. Take alpha beta belonging to L of S and A comma B belonging to F. So, alpha beta are elements of L of S. So, they should look like linear combination of elements of S. So, that is why I am writing alpha as A1 alpha 1 plus A2 alpha 2 etc. An alpha n, and beta also same, but I am only changing the scalars B1 alpha 1 plus B2 alpha 2 etc. Bn alpha n, where A comma B, A is B is belong to F and alpha is belong to S. Now find out the combination. It again looks like some A dot alpha 1, some A dot alpha 2, etc. AAN plus BBN alpha. It is again a linear combination of vectors of S. So this again belongs to L of S. So from the necessary and sufficient condition which we proved just now, L of S is a subspace of phi. So for the sake of understanding of this linear combination, just look at this problem. So in case of R cross R, express the vector 2 comma 3 as a linear combination of 1 comma 0, 1 comma 1. So use the definition, write it as a linear combination 2 comma 3 equal to A into 1 comma 0 plus B into 1 comma 1. So if you equate first coordinate and second coordinate, you get A plus B equal to 2 and B equal to 1. So solving that, you get A equal to 1 and B equal to 1. Finally, if you write 2 comma 3 as 1 into 1 comma 0 plus 1 into 1 comma 1, means if I want to reach 2 comma 3 in the space of R cross R, I have to travel 1 unit along the vector 1 comma 0 and 1 unit along the vector 1 comma 1. So this is the interpretation of linear combination, right. So hope so you understood the concept of linear combination of vectors. So finally, let me conclude. So in this class we defined what was a vector space and we understood some points and also a simple theorem about vector space, and we also did some examples and some problems for homework also. The second topic was subspaces, where we defined what was a subspace and we provided some examples and some verifications, and also very important necessary and sufficient theorem which we proved just in this class. So note that students, please note that this is a very important theorem for exams also, it will be asked, the proof also, state and prove. And finally, in the third topic we verified that we defined what was a linear combination of vectors and we observed some properties of linear span L of S and a simple problem. So for more details you can look at any textbook of vector space or linear algebra for that matter, and you can get good knowledge. So I wish you all the best. Thank you and so on.